as well as the steel table. Okay, we need both. Okay, the recording has started. Okay, good afternoon, guys. So let us go with the next example. Before we go, just I want to make sure you have the code book, that is IS 800, and also the steel table, preferably by KLV Ram, with you as of now. Okay, because we need both. Going to the next example. 1 second. So the problem says a tie member consisting of an ISA 80 by 50 by 8 millimeter is welded to a 12 mm thick gusset plate at site. Keep in mind. So design welds to transmit load equal to the design strength of the member. Okay, first let us understand the problem. This is a tie member. Tie member is nothing but the member which is subjected to a tensile force. So that is pulling. Okay. And what is the section? We are using an angle section of dimensions 80 by 50 by 8 millimeter. Okay. And the longer leg, that is 80 millimeter length leg, is connected to the gusset plate of 12 mm thick. Is it clear to you? And the material for the gusset plate and for the angle is of the same thing, that is Fe 410 grade steel material. Okay, so we need to design the welded connection. That means we need to find out what are the sizes of the weld we need and what are the lengths of the weld we need. So here we can provide welds in two different ways. So we can provide welds here in the opposite directions. Okay, here these are two parallel welds. Okay, and another way is weld here and weld here and weld here. Okay, so and also it says thick gusset plate at site. Remember, because the welding is being done at the site. Okay, design welds to transmit load equal to the design strength of the member. So here the force is not given. The design force or design load is not given acting on this member. Instead, what the problem says is find out what is the design strength of this member. Find out at what load the material is going to yield or the angle is going to yield. Okay, for that force, we need to design the welded connection. Okay, and we are going to solve this problem in two ways. In one case, we are going to provide welds in the two opposite sides or two opposite faces, and in the second case, we are going to provide the weld on all three sides. Okay, so if you look here, I applied PU value exactly along the neutral plane of the angle. This is the neutral plane. Okay, so when you look from this side, this is what you are going to see, and if you extend this neutral plane to the cross section, the same neutral plane is going to be neutral axis, and this is D2 value, that is from the bottom of the shorter edge to this line, that is called the neutral axis depth, and from the top, this is D2, D1 is the neutral axis depth. So where do we get all those values? So for that, please open the steel table. Okay, so keep flipping the pages. Of course, first you are going to get rolled steel beams. Okay, further you'll have some more pages. So keep going and stop at page 20 of KLV Ram, steel tables by KLV Ram. See, it says rolled steel equal angles. So dimensions and properties, that's what is given. Do you see that? So it says ISA 20 by 20, ISA 25 by 25, etc. These are all equal angles because the leg sizes are 20 millimeter by 20 millimeter, 25 millimeter by 25 millimeter, etc. So, but in our case, the angle size is 80 by 50 by 8 mm thick. So this means this is an unequal angle. So you are not going to get the information we need on page 20. Okay. If you go to page 22, again, that covers equal angle section. So let us go to page number 24. Against rolled steel unequal angles. So this is where we have to look at. So unequal angles means it will have two different leg sizes. Okay, what is our section? 80 by 50 by 8 millimeter. So if you go to the leftmost column where it says the designation ISA 30 by 20, ISA 40 by 25, etc. At the last item, that is ISA 80 by 50. That's what we have here, 80 by 50. And what is the thickness? 8 millimeter. So go to the third column where we see the thickness. So we see the thickness for 5 millimeter, 6 millimeter, 8 millimeter, and 10 millimeter. So ours is 8 millimeter thick. Okay. So area of cross section of that is 978 millimeter square. Do you see that? 978 millimeter square. So after this, go up, look at the figure. Look at the figure at the top. So longer leg is represented by capital A and shorter leg is represented by capital B. So for longer leg, so from the bottom, the depth of the neutral axis, that is the distance of the XX axis from the bottom, is represented by CXX. Do you see that? Similarly, from the top, it is EXX, small e, XX. So of course, if you add EXX and CXX, you are going to get A, which is the total depth of the longer leg. Here in this case, it is 80 millimeter. Okay. So again, if you come back to ISA 80, 50 by 8 millimeter, so what is EXX value? EXX value is 52.7 millimeter. Do you see that? And what is CXX value? CXX value is 27.3 millimeter. First one is CXX 27.3 millimeter and EXX is 52.7 millimeter. So you have to go ISA 80 by 50 by 8 millimeter thick and go horizontally along that line. You get, again I repeat, CXX equal to 27.3 and EXX equal to 52.7. Okay. So instead of calling EXX and CXX, what I have done is I have called that as D1 and D2. So what is D1? D1 is this value, that is nothing but EXX value, that is 52.7 millimeter. Similarly, D2 is CXX, that is C suffix XX, which is equal to 27.3 millimeter. Of course, D is the overall depth of the angle. That is the dimension of the longer leg, which is 80 millimeter. That's what I have written. And small a equal to 978 millimeter square. That is the area of cross section of the angle. Okay. And I hope this is clear to you. So going further, the problem says design welds to transmit load equal to the design strength of the member. So what is the design strength of the member? So that is, the design strength of the member is the strength at which the angle starts yielding. Okay. So what is the formula to get the design strength? So for that, go to page number 32 of the code book. Page number 32, 6.2. Please go there. In the second column, it says design strength due to yielding of cross section. That's what we need to consider. So TDG equal to AG Fy divided by gamma MO. Are you there? So in this case, we need to substitute the values. AG is the gross area of cross section of the angle. So that is 978 millimeter, which I got from here. That is small a equal to 978. That's what I'm using here. And Fy is the yield strength of the angle material. So for Fe 410, Fu equal to 410 Newton per millimeter square and Fy equal to 250 Newton per millimeter square divided by gamma MO. What is gamma MO? So where did we get gamma MO? So go back to page number 30, table 5. Table 5. So first line itself, a resistance governed by yielding gamma MO. So the partial safety factor is 1.10. Okay, that's what I have used, 1.10, and divide the whole thing by 1000 to get the TDG value equal to 222 kilonewton, or in other words, PU equal to 222 kilonewton. That is the force at which the angle section starts yielding. Okay, so we need to design the connection, that is the welded connection, to take care of this design force of 222 kilonewton. Okay, so again, if you come back up, PU equal to 222 kilonewton, and that force should be transferred to the gusset plate by connecting the angle to the gusset plate, and we have to connect those two things using welds on two sides. Okay, so here we need longer leg, or longer weld on this side and shorter weld on this side. The reason is, if you come here to the cross section, we have some area here and some more area gets added to this weld. So this is the area which is transferring the force to this gusset plate through this weld. Okay, so we need this much of weld for this. Next, so through this weld, we are going to transfer P1 value. In this case, P2, and here we are going to transfer P1 value, which covers the force in the lesser area. Lesser area means lesser load we are going to transfer. So lesser load means we are going to need lesser length of the weld. And of course, we are going to give some return weld here as per the codal recommendation, but for strength consideration, we are not going to consider this. Okay, so we need to find out what is LW1 value we need, and we need to find out what is LW2 value we need. Okay, so for that, the first thing we are going to do is to find out what is P1 and what is P2. Of course, P1 plus P2 should be equal to PU value. Okay, so P1 plus P2 equal to PU, which is equal to 222 kilonewton. Then I'm going to take moments of all the forces about the weld LW2. So that means I'm going to take moments of all the forces about this weld, that gives P1 multiplied by D, okay, with minus sign because it's counterclockwise, plus PU multiplied by D2. That should be equal to 0. So find out P1. Whether you take about this or about this, it doesn't matter. Finally, you'll end up getting the same answer for both P1 and P2. But I'm taking about this base. Okay, P1 multiplied by D, that is a perpendicular distance from this line to the line of action of the force P1 with minus sign because counterclockwise, plus PU multiplied by D2. Again, I'm saying it 2 times, guys. So if you look here, this is what we have. And that should be equated to 0. I forgot to add 0. Please put equal to 0 here in this place. Let me make a correction in my notes. Yeah, I have made it already. Okay, so that should be equated to 0. So PU is known, 222. D2 is known, D1 is known, D is known. So find out what is P1. P1 equal to 75.78 kilonewton. And of course, P2 equal to 222 minus P1. P1 is 75.78. So that means P2 equal to 146.54 kilonewton. So what it means is P1 is 75.78. So P2 is 146.54. So that means we are trying to transfer the load of 75.78 through this weld and the remaining 142 something through this weld, 142 point something kilonewton through this weld. Obviously, we need longer weld here and shorter weld here. Okay. So these are the two forces, P1 and P2. Now, coming to the length of the weld, before we know what is the length of the weld, we need to find out, or we need to fix what is the size of the weld we need. Okay, for that, please open page number 78 of the code book. Please open page number 78, table 21. I hope you are on that page, page 78, table 21. In the second column, it says minimum size of first run or of a single run fillet weld. So we always care about single run fillet weld. Okay. So we don't worry about the second run, third run, etc., because that rarely happens. Okay. For single run fillet weld, so the minimum size of the weld. So thickness of thicker part. So here, again, I will go back up. So what is the angle thickness? 8 millimeter. So what is the gusset plate thickness? It is given 12 millimeter. So which one is thicker? 12 millimeter thick is thicker than 8 millimeter thick of the angle. So again, if you go back to the table, see thickness of the thicker plate, plate, that is our 12 millimeter falls between 10 millimeter and 20 millimeter. The first line is 0 to 10. The second line is over 10 millimeter and up and less than equal to 20 millimeter. So what is our case? What is the thickness of the thicker plate? 12 millimeter. So for 12 millimeter thick plate, what is the minimum size of the weld we need? That is 5 millimeter. Again, along the same line in the table, 5 millimeter is the minimum size of the weld. That's why I have written S is the size of the weld. S is the one we are going to represent the size of the weld width. So S minimum is 5 millimeter. Then comes what is S maximum. What is the maximum size of the weld we can go? So for the maximum size of the weld, if you go to the next page, page 79, in the second column, you will see 10.5.8.2, where the fillet weld is applied. I'm going to read that. Where the fillet weld is applied to the rounded toe of a rolled section, the specified size of the weld should generally not exceed 3/4 of the thickness of the section at the toe. So it says, refer figure 17b. Okay. Go to the next page. On page number 80, on the top, you will see figure 17b. So this angle, if you consider any angle, this is the rounded edge. This is also the rounded edge. Okay. So as per the code and as per figure 17b, the maximum size of the weld we can put is 3/4 of the thickness of the angle section. So that is 3/4. What is the thickness of the angle section? 8 millimeter. So S max, that is the maximum size of the weld we can provide, is 6 millimeter. So minimum is 5 millimeter, maximum is 6 millimeter. So you can provide one of these two. That is good enough. Okay. So here I have chosen 6 millimeter. If you want to choose 5 millimeter, go ahead and find it. Put 5 millimeter, and you may need a little bit longer length of the weld. So here I have chosen 6 millimeter as the size of the weld. Okay. Now once the size of the weld is over, then we need to find out what is the length of the weld we need. Okay. We don't know what is the length of the weld we need. So for that, what we have done is, I have called that as LW1, L suffix W1 is the total length of the weld, and this weld will have again throat. So throat thickness multiplied by the length will give you the throat area, and that is the area that is offering resistance against the force P1, or that is the area which is transferring the force P1 to the gusset plate. So you can say in both ways. So what is the design strength of 6 millimeter size weld of length LW1? That is throat area. What is the throat area? Throat thickness multiplied by LW1. So for a moment, I'm going to take to the previous page, this one. See here. So this is the weld we are going to consider. This is 45, this is 45 degree, and length of the weld runs perpendicular to the paper. So that is shown in 3-dimensional way. Okay. So from here, you are going to draw a line perpendicular to this. That is the throat thickness. That is given by 0.7 times S, where S is the weld size, multiplied by the effective length of the weld. Effective length of the weld will give you the throat area. So this is the throat area, and this is where, or along this plane, the weld is going to fail due to shear. Okay, that's why I call this as failure plane or the throat area. So we need to multiply this throat area by the design strength of the weld, FWD. Okay, so I'll go further down. I'll go back to the problem. Okay, so what is the throat area? That is the length of the weld multiplied by the throat thickness multiplied by the weld design strength of the weld. So where did we get the design strength of the weld? Again, go to page number 79. Design strength of the weld is FWD equal to FWN divided by gamma MW. So go to first column on page 79, go down. It comes under 10.5.7.1.1. Okay. So FWD, weld, D stands for design, W stands for weld. So FWD equal to FWN divided by gamma MW. So where FWN equal to FU divided by √3. Okay. So that is what I have substituted in this. This gives the design strength of the weld per unit area, that is per millimeter square, multiplied by the throat area will give you the design strength of 6 millimeter size weld of length LW1. Okay. So coming to FU by √3, FU is 400 ton and LW1 is the value we need to find out. And what is the throat thickness? Weld size multiplied by 0.7. This is sine 45 degree. Okay, or 0.7 times 6 will give you the throat thickness. The whole thing will give you the throat area. So FU is 410 divided by √3 multiplied by 1 divided by 1.50. So gamma MW is 1.50. So why I have taken 1.50? Again, I will go to the problem. In the problem, if you read it, design welds to transmit load equal to the design strength of the member. Okay. And another is Fu 410 grade steel is welded to a 12 mm thick gusset plate at site. At site, remember. So we are doing the fabrication at the site, not at the workshop. So at site means, so go to page number 30, table 5. Okay, go to page number 30, table 5 of the code book. So what is, go to the last line under D, it says weld gamma MW equal to, for shop fabrication, that is shop welding, it is 1.25, and for field fabrication, that is field welding, it is 1.50. So in the problem, it is clearly given that the fabrication is done at the site. That means field fabrication. Therefore, gamma MW equal to 1.50. That's why I have taken 1.50 here. Okay. Once you do that, so finally, after simplification, I got this value 0.663 LW1 is the design strength of the weld of length, effective length LW1. Okay. So what I do is I'm going to equate this equation with P1 value. What is the value of P1? 75.46. What is that P1? That is the force we are trying to transfer. That is a design force we are trying to transfer through this weld to the gusset plate. So this length should be adequate to take care of P1 value. So by equating equation 3 with P1 value, so this is the value we have. So finally we are going to get LW1 equal to 114 millimeter. That is the minimum effective length of the weld we need. Okay. But however, the code says the actual length should be at least LW1, that is a minimum effective length, plus 2 times S, that is where S is the weld size. Where it is given? Again, if you go to page number 78 under 10.5.4.1, okay, it says the effective length of fillet weld shall be taken as only that length which is of the specified size and required throat thickness. Again, page 78, second column. So in practice, the actual length of weld is made of the effective length shown in drawing plus 2 times the weld size. At least 2 times the weld size. Okay, but not less than 4 times the size of the weld. Of course, we are going to maintain that. So total length or the actual length of the weld we are going to provide is minimum effective length of 114 millimeter plus 2 times the size of the weld. Size of the weld is 6 millimeter. So total is 126 millimeter. So the minimum length of the weld we need on this side is 100. Minimum total length of the weld we need is 126 millimeter. But however, we are not going to give that fractional value. Instead, we are giving a length of 130 millimeter on the top side. Similarly, we need to give weld on the bottom side as well. So what is the force the bottom weld has to withstand? That is 146.54 kilonewton it has to withstand. So what is the design strength of 6 mm size weld of length LW2? That is the effective length LW2 multiplied by the throat thickness will give you the throat area multiplied by the design strength of the weld, which is Newton per millimeter square. So all the values remain the same, just like in this case. So the only variation is LW2. So we need to find out LW2. Now we are going to equate LW2 to this P2 value now. 146.54, 146.54. So once we equate that, the minimum effective length we need is 221 millimeter. Therefore, actual length we need is LW2 plus 2 times the size of the weld. So that is 233 millimeter. So we are not going to provide 230 millimeter. Instead, we say 240 millimeter. Is this clear to you? So when it comes to 240 millimeter, 130 millimeter. So if you look here we are going to provide 130 millimeter length of the weld minimum, and here it is minimum of 240 millimeter. So to take care of these two forces, and the combined value of P1 and P2 is Pu value, which is 222 kilonewton. Okay. So once that is done, we need to do some extra check. So as per the codal recommendation. So what is the check we are going to do? So here, minimum lap of the joint. Lap is nothing but, if I go back, so from here to here, what is the length? That is the lap length. That means this is the length of the angle, okay, which is going to be in contact with the gusset plate. Okay, what is the minimum lap we need as per the code? So that means, as per the code, minimum length of weld on either side. Lap is nothing but here, what is the minimum length of the weld? Should be greater than equal to transverse spacing between longitudinal welds. Okay, this is as per 10.5.1.2 last sentence, page 78. So that means transverse spacing between longitudinal welds means, say, look here, what is the transverse spacing between this weld and this weld? That is 80 millimeter. This is the angle we have. Longer leg is 80 millimeter here. So the spacing between the transverse welds is, between these two, parallel welds is 80 millimeter, and minimum length of each part of the weld should be at least equal to 80 millimeter. In this case, we are providing 130 millimeter. Here we are providing 240 millimeter. So obviously 130 millimeter is greater than 80 millimeter. So we are okay. In case, say for example, we got LW1 equal to say 60 millimeter, for example, 60. So of course 60 millimeter is less than 80 millimeter. Then in this case, go ahead and provide at least 80 millimeter. Okay. So in this case, we are okay. Okay, that completes the problem. So let us provide a 6 millimeter weld of length LW2 240 mm on the bottom. Finally, write a figure like this. Write a figure like this. Show this. Okay, show LW2 total length equal to 240 millimeter, LW1 equal to 130 millimeter, and show a return of 2S. Okay. In the next problem, I am going to discuss about this return value. So this return should be at least 2S, where S is the size of the weld. So in this case, for 6 millimeter weld, it is 2S equal to 12 millimeter. So when you weld, when you give a return, so the length of the return should be at least 12 millimeter. If it is beyond that, that's fine. So this is provided just to avoid stress concentration at the corners. So going with the next example, see here, design a fillet weld for the angle section of the above example if the weld is to be done on its 3 sides. This time, what we are doing is, we are not providing welds on 2 opposite sides. Instead, we are providing welds on 3 sides. Okay. As far as PU is concerned, it is the same, 222 kilonewton. Okay. And we need to find out what is the design force we are transferring through this weld, and what is the value from here, and what is it from this side. That means we need to find out P1, P2 and P3 values. Okay, P1 plus P2 plus P3 equal to PU, which is 222 kilonewton, which we calculated in the above example. So D is 80 mm. Again, from the previous example, D1 is 52.7 millimeter, D2 is 27.3 millimeter. So PU equal to 222 kilonewton. So we have P1 plus P2 plus P3 equal to 222 kilonewton. Here we have 3 unknowns, but we have only 2 equations of equilibrium. So what are the 2 equations of equilibrium we have? This is one equation, and the other equation by taking moments of all the forces about this. So that way we have 2 equations, 3 unknowns. Definitely we cannot solve the problem. Okay, so at least one unknown out of these 3 should be known. Then the number of unknowns will get reduced to 2. Then we can solve the problem. So when you come here, we don't know the length LW1, which we need to calculate. Similarly, we don't know the length here LW2, which we need to calculate. But we know this length of the weld. So this length of the weld is 80 millimeter. That is the leg size. Okay. And we know the size of the weld. So what is the size of the weld we have taken? Here. 1 second. So P1 plus P2 and 53.2. Okay. Coming to this. So strength of the weld of length D equal to 0.663 LW. Just like in the previous example. So here D equal to LW equal to 80 mm. So this is the size of the weld. We know the length of the weld on this side and also the size of the weld. That way we know the throat area multiplied by FWD value will give you the design strength of this weld, and that acts, resultant of that force acts exactly in the middle. That is P3 value. So if you look here, so strength of the weld of length D equal to 0.663 LW. How did we calculate? Again, throat area multiplied by FU by root 3 multiplied by 1 by gamma MW. So once you do that, you will get this. Okay. So that is, in this case, this is LW, effective length of the weld. So that is equal to D. Okay. So substitute D equal to 8 mm. Once we do that, so we are going to get this value, 53.04 kilonewton. What it means is, see, when you provide weld, the design strength of the weld of length 80 millimeter is 53.04 kilonewton. Is it clear to you? So once this is calculated, go back and substitute the value of P3 in this equation. So we are going to get P1 plus P2 equal to 168.96 kilonewton. That means 53.04 kilonewton is taken care by this weld, and that acts exactly in the centroidal area. Okay. And the remaining loads or force should be carried by P1 and P2. So we need to find out what is P1 and P2. So by taking moments of all the forces along LW2, that is along this, we are going to get P1 multiplied by 80 mm with minus sign, P3 multiplied by D by 2, that is 40 mm. Okay. And P3 value is known. Next, plus Pu multiplied by D2 value. That should be equated to 0. So if you look here, that should be equated to 0. Minus P1 80 minus 53.04 multiplied by 80 by 2 plus 222 multiplied by 27.3. That should be equated to 0. So I got P1 value equal to 49.24 kilonewton. So by substituting P1 value in this equation, we get P2 equal to 119.72 kilonewton. Now we know. So what is the value of P1? What is the value of P2? And what is the value of P3? Okay. So coming to this, what is the length of the weld we need for P1? Again, if you remember, throat area multiplied by the design strength of the weld should be equated to P1 to find out what is the effective length we need. Is it not? So it is 0.663 LW2. 0.663 LW2, yes, we got this value from the previous steps in the previous problem. Even if you do the calculation, you will end up getting this value. That is the throat area multiplied by FWD value. Okay, you are going to get this, and that should be equated with P1 value, that is 49.24 kilonewton. So that way we got the effective length of the weld. Minimum effective length of the weld is 74.27. So what is the actual size of the weld we need? 74.27 plus 2 times the weld size, 86.27. Of course, we are not going to provide 86.27. Instead, we are going to go ahead and provide 90 millimeter length weld of size 6 millimeter. Is it clear to you? That means we are providing 90 millimeter length. Okay. Next. Similarly, for load P2, what is load P2 or force P2? 119.72 kilonewton. So 0.663 LW2 should be equated to this value. And we got that value equal to 181 millimeter. Okay, finally, the total length of the weld at the bottom is 193. Of course, we don't provide 193, we provide 200 millimeter. So, coming back to this length, total length we are providing is 90 millimeter. Of course, this is 80 millimeter and this one is 200 millimeter. So, for this case, we don't have to check for minimum lap length of 80 millimeter. So, as per like this, see, we are going to provide or we are going to check for a minimum lap length only when we are providing weld in the opposite directions, in these two directions. Okay, so because we are providing weld in all the three directions, you don't have to apply this check in this case. Is it clear to you? Okay, so coming to giving a return, I'm going to discuss in this problem. So this completes the problem. Okay, and again write a neat figure like this. Show the dimensions: 90 millimeter, 200 millimeter. This is 80 millimeter of size 6 mm size weld. Okay, that completes the problem. Then we'll go ahead with the next problem. Next problem is a tie member of a truss consists of double angle section, each of 80 by 80 by 8 millimeter, welded on the opposite side of a 12 mm thick gusset plate as shown in figure. Okay, design a fillet weld for making the connection in the workshop. Remember, in the workshop means what is the value of gamma MW? As per table 5 on page 30, gamma MW value is equal to 1.25. So the factor tensile force in the member is 300 kilonewton. That means, see, if this is a truss member, so a truss is subjected to different kinds of loads. So depending on the loads, so each member will subjected to different force magnitude. Okay. So after analysis, we found that this member is subjected to 300 kilonewton design force. So design force is obtained by multiplying the service force, which is 200 kilonewton by 1.5, that is equal to 300 kilonewton. So this is design force or ultimate force or factored force in the member is 300 kilonewton. You don't have to multiply this by 1.5 because it is already multiplied. Okay, you take this force as it is and design the connection to withstand this design force. And we are providing two angles. So what is the size of each angle? 80 by 80 by 8 millimeter. Okay. So this is an equal angle of thickness 8 millimeter. And those angles are provided back to back. So this is one angle, that is this angle you are seeing, and there is one more angle on the other side of the gusset plate. Okay. So there are two angles. So that's why I have written 2 PU equal to 300 kilonewton. So once I find out PU, which is equal to 150 kilonewton, each angle is carrying a force of 150 kilonewton design force. So for that 150 kilonewton, we need to provide the welds along the edges in two parallel directions. Okay. Then same thing you repeat on the other side. You don't have to do the calculation, but you are going to provide the same weld on the other side of the gusset plate. Okay. So in the examination, if nothing is mentioned, you can provide welds on these two sides, or you can provide welds on this side, on this side, on this side. That is on three sides. Okay. The choice is yours if nothing is mentioned. If they say provide welds on two parallel sides, so this is what you are going to do. If the problem says provide welds on all three sides, then you'll have to provide welds on these three sides. Okay. Here, because nothing is mentioned, I am taking this way. Okay. Coming back to this. So if you go to steel table, page number 22, please go there. Are you on that page? So steel table, page number 22. If you go to the next column, designation is ISA 8080. That is ISA 80 by 80. Under ISA 80 by 80, we have four thicknesses: 6 millimeter, 8 millimeter, 10 millimeter, and 12 millimeter. So ours is 8 millimeter thickness angle. And what is the area of cross section of 8 millimeter thickness angle? Each angle, that is 1221 millimeter square. Do you see that? 1221. Okay. Going further, CXX equal to 22.7 millimeter and EXX equal to 57.3 millimeter. Do you see that in the steel table? So I have called those EXX and CXX values as D1 and D2, and I have written D1 equal to 57.3 millimeter, D2 equal to 22.7 millimeter. Of course, D equal to sum of these two, 80 millimeter. That is the total depth of the angle. Okay, because each angle is of equal length, so it doesn't matter which this one leg you are going to connect. Okay. Next, 2 PU equal to 300 kilonewton. Factored load on each angle equal to PU equal to 150 kilonewton. And the next thing is we need to fix what is the size of the weld. So for that, what is the minimum size of the weld and what is the maximum size of the weld? So what is the minimum size of the weld? S minimum. That is page number 78, table 21. Again, we are going back to that page. Table 21. So what is the thickness of the thicker plate? 12 millimeter. That is the thickness of the gusset plate that falls between 10 millimeter and 20 millimeter. So for 10 millimeter and 20 millimeter, what is the minimum size of the weld? 5 millimeter weld is the minimum size. Again, what is the maximum size of the weld? Again, go to page number 80. Look at figure 17B on the top. So that is equal to maximum thickness is 3/4 the thickness of the angle. So the thickness of the angle is 8 millimeter. 3/4 of 8, that is equal to 6 millimeter. So minimum size is 5 millimeter, that is S minimum. And the maximum size is 6 millimeter, that is S maximum. So you can take one of these two values. So in the previous example, what I did was I took 6 millimeter. For a change, I've taken a value of 5 millimeter in this case. What in case if the value falls between 4 millimeter and 8 millimeter? You can take the weld size of any size between 4 and 8. 4 millimeter, 5 millimeter, 6 millimeter, 7 millimeter, and 8 millimeter. Any of those sizes you can take. But in this case, 5 is minimum, 6 is maximum. So I'm taking 5 millimeter as the size of the weld. So if this is of the weld shape, okay, so This is the weld size or the leg size of the weld, which is S equal to 5 millimeters. Similarly, this is 5 millimeter, and this is the throat thickness, that is equal to 0.70 times the S value. Okay, so right now to calculate P1 and P2, so we are going to apply the same logic the way we did for the previous problem. Okay, so find out what is P1 and P2. Again, if you look here on each angle, so this weld is transferring a force of P1 and this weld is transferring a force of P2. Of course, length of the weld here is longer than the length of the weld here, as you all know, because this weld is transferring more force because of the more area. Okay, it's, I mean, whatever the area here, okay, whatever the force in that area is going to be transferred through this weld, and when it comes to this weld, it covers only lesser area, means lesser force. That's why we need lesser length of the weld. Okay, so find out what is P1 and P2 with this. So I'm going to end this class. I'm going to continue tomorrow. Okay, and we will meet at the same time tomorrow. See you guys and take care. Bye for now.